Okay, good afternoon. Oh, good morning. How are you today? Okay, I was hoping that I could pick your brain on some very interesting topic. So it's understanding throughput and common misconceptions that what is the actual or real throughput, what people understand as a throughput, and all the things that we usually see at MikroTik support, because as you know, some of our products are basically for home users, so we also get a lot of questions, very basic questions. But when you look deep enough into them, you understand that even some network specialists don't get all the things right for the first time. So basically, I made this presentation for several reasons. Main reason is to help you to take a deeper dive or different look into some well-known basic concepts and to understand that they are not as basic as you think. Of course, to allow you to configure MikroTik equipment so that it can do more. Encourage you to upgrade to the newest router OS versions and use newest features. And of course, the main thing for me is to reduce the amount of support tickets to the support@mikrotik.com. So in any case, if somebody will send in a question about this topic, I can always link to this video presentation and say, watch this. So those who have written to me previously, you know that I do that already for years. And some of you have been sent to throughput videos, to fast track videos, and so on. So that thing works for me. So I will keep at it and continue in that regard. So let's just jump to the basics. So what is throughput? So throughput is a measure of how many units of information system can process. So main words here, in a given amount of time. So if we're talking about data transmission or network throughput, is amount of data successfully transferred from one place to another, and usually we measure it in bits per second. So successfully. So in other words, if we take a look at the router throughput, we just need to sum up all the outputs together, because all the data that was successfully sent out of the router successfully went through the router, so that is a throughput. So sum of all those outputs that you can see. But then the thing gets more interesting. So if you, for example, take a hub AC and you send 1.5 gigs into it, you might get out something like 750 megs of traffic out of it. But if you send 950 megabits per second in, you will get almost all of it out. So, question, what is actual throughput in this case? What is the throughput of the device? Is it 750 or is it 950? So, we also tend to think that. So, in all our measurements that we publish on our homepage, so these tables, all products have tables like these on our homepage. We try to find the amount of traffic that result in a loss less than 0.1% of traffic. So, and we usually test it with that amount of traffic. So, but to understand the throughput, one of the first limitations that network devices have, is considered as a physical limitation or wire speed limitation. So link or wire speed refers to the rate of data transferred given on this technology. So we have Ethernet technology since the beginning of time, and now we have 6 speeds. So 10, 100, 1 gig, 2.5 gigs, 5 gigs, and even 10 gigs on Ethernet. SFPs, so you have 1 gig SFP, 10 gig SFP pluses, 25 gig SFP 28s, and then there are QSFPs, so 40 and 100 gigs. So those are link speeds or wire speeds. But when we're talking about wire speed, we also refer to it as an adjective. So that describes that hardware or function that supports data transfer without slowing it down. So if some data transfer, for example, switches, as Lorenzo just explained in previous presentation, yes, switches, when you use a hardware solution, do the switching in wire speed. So that's why this is used here as an adjective. So don't be confused with wire speed as a cable speed. So two different things. So usually the functions embedded in microchips, so we know them as ASICs, are more likely to run at wire speed than functions that implemented in software. So currently, basically, we have switch chips that are capable to transfer data at wire speeds, and the impressive set of features that come with them. When we're talking about wireless wire speed, name is interesting, but others know it as data rates. Those are maximum theoretical wire speeds that determined by wireless protocol. So in here you can see AC and N standards, and there's some impressive numbers up to 3.5 gigabits per second even. So it depending on number of streams, modulation, channel width. So, but wireless guys will tell you more about it. And also we need to cover the newest stuff is the 60 gigahertz. Grayed out are actually ones that we don't support at this moment. They might be added in some future 60 gigahertz software or hardware updates. So, but black ones we have in our upgrade. So why I'm showing you, because most of the clients, when they take a look at other manufacturer boxes, see these things written on them. So AC quad stream plus with AD Wi-Fi up to 460 wireless speed. So another box says something like similar. So beamforming with 2.4 and 5 gigahertz, and you see some of these, so on. So of course, if the newbie just purchases a device, they expect to see the resulting sum of these numbers and so on. So basically, that's just. So what are those numbers? So lies? Well, not exactly. Also, switches. Many manufacturers really love to put these numbers over here for their switches. So gigabits per second on. So how can you get 640 gigabits per second on 24-port switch or something like that? So, well, basically, the right answer, it's not lies. It's actually called capacity. So network device capacity is measure of a device structure's bandwidth. So for example, if you take a look at our WAP-G, so WAP-IC, so it has a 5 gigahertz triple chain AC wireless, 1.3 gig, 2 gigahertz dual chain N wireless, 0.3 gig, and 1 Ethernet, gigabit Ethernet, so 1G. But you all know that wireless are half duplex, but wired connection is full duplex. So nothing stops marketing person to actually multiply the wired speed by 2. So the capacity of WAP-G in this case would be 4.6 gigabits per second if we apply the same logic as it was applied in these marketing numbers over here. So if we take a look at the switch, so 309, which has a 8 10G ports, so 8 times 10G, and 1G, and of course it's full duplex, so we can multiply it by 2. Then we get 162 gigabit per second capacity that you could put on these switches. So we started to get some fancy emails that competition offers faster switches than we do because their numbers are bigger on the box than ours. That was like, at that point we decided, oh, what the hell, let's just so let's just have it. So we just added another table which indicated all the layer 1 wire speed and layer 2 wire speed. So we put all the possibilities that other competition, other vendors put in on their boxes. So we just made a table of all these numbers. So and if you notice that on layer 1, yeah, throughput is exactly the half of the capacity, because you know throughput is leaving traffic, a capacity is just a duplex times 2, so that's the difference. But we also added just screw some brains up, layer 2 throughput and capacity, so that people start to think about those numbers, not just reacting which number is bigger. So many of you, when we're talking about OC layers, always think about layer 3, layer 2, but you always forget about what's happening on layer 1. So layer 1 also adds a header and a tail to the packet, and also takes something of the wire speed. So you cannot use the all wire speed for the data. So Ethernet is a self-clocked digital protocol. So the clock is synchronized by preamble field that provides a predictable 7 bytes long signal for Ethernet receiver, followed by 1 byte start of the frame delimiter, so 8 bytes before we send the packet. And then there's a specific minimum period that there must be silence after the packet was sent, so a gap. And it takes 12 bytes. So we take a look at the picture. So there's a 7-byte preamble, 1 byte start of the frame, and in the end we have interframe gap of 12 bytes. So for any packet that you send, you basically need 20 bytes to encapsulate it from electrical signal on the layer 1. So, and that's how the stream of packets look like. So if we take a look at the Tcp Ack packet, which is the smallest packet that we usually use, so it's around 40 bytes by default. So it's actually historically too small. So it needs to be padded to 46 bytes to reach the minimal Ethernet payload size. And then you need to add layer 2 header. So as you can see, this is layer 1. Red one is layer 2, so Ethernet header and frame checksum, another 18 bytes. Then there's the IP header, another 20 bytes. Then the TCP header, and the actual data that you're sending here is quite small. So if we take a look at this packet over here, if you want to send only TCP Acks, you actually can use 47.62% of your actual wire speed for your TCP data. So if your clients are saying, I'm not getting my full gigabit or something, that might be related to the fact that it's utilized to encapsulate in OC layers that many of you have forgotten belong below the layer 2 and layer 3, because there's also layer 1. So of course the picture is not so bleak if we talk about 1500 byte packets, for example UDP ones. So then the same logic applies, and you have a 97.5% utilization of the wire speed. So, but of course the reality is somewhere in the middle. So if you want to find what's the number for you, if you, for example, use a fast track, the easiest way is just go to the IP settings take a look at these two numbers and divide the amount of traffic by the amount of fast-tracked packets to see what's your average size of the packet. So this is actually mine. So my number is close to 96.4% wireless speed efficiency with my packet sizes. Of course, there's another option that we can talk a few slides about, gigabytes and gigabytes. So there's a difference. Many confuses these two also. So there's also some numbers get lost over there, especially on hardware side, on hard disk size. That's, I think, the biggest one that you usually see, not so much in networking. So that's the first misconception. So people see the marketing numbers, see the wire speeds, and then look at the actual performance speeds, and they see the difference. So the major loss usually is in this padding stuff and fancy marketing numbers. But let's ask some tricky question. So what is 1 gigabit per second speed really? Is it same as 1 megabyte per millisecond? 4,000 milliseconds. Or is it 1 byte per microsecond all the time? So what is actually this 1 gigabit per second? Second in computer terms is a very, very big amount of time. Lots of things can happen in a second. So modern processors have lots of computations happening in the second. So how can you actually determine, for example, if you want to limit something, you want to limit it to 100 megabits per second. That's a very broad time frame to limit it. So how a router can know what will happen in the future or what happened before to apply this limit. And if you apply this limit, so does it actually work? Why can I see, for example, 22 megabits per second on my speedtest.net result when I have a specific queue that sets only 20 megabits per second? So, and is there any difference if I only have a 60 megabit per second connection? So my ISP limits me to 60 megabits per second, and he offers me to have a fast Ethernet or gigabit Ethernet. Are there any difference between these two if I only limit it to 60? So these questions are tricky. So that's why, to explain them properly, I will try a different approach. So as one of my favorite teachers in a university said, if you cannot explain it simply, then you cannot understand it properly. So let's scale up stuff. So let's take a little dive into imagination world. So imagine that Ethernet is a highway. Ethernet frames are cars and trucks, different sizes, different engine sizes. So frame size is actual engine size. So let's replace queues with tunnels and queue size with our usual everyday traffic jam size. And of course, now we'll not be talking in seconds, we'll be talking in hours. So let's imagine we have a tunnel. So tunnel has a limited ventilation, so it can handle only total engine size sum of 3,600 liters. By the way, why do you use liters in engine size here? Why it's not gallons as everything else? Because I was Googling, do I need to change this presentation for the US measurements? But it turns out you have liters everywhere. So. Okay, so I will stick to the liters for this presentation. So the tunnel limitation is 3,600 liters per hour. So basically that's engine displacement liters per hour. So how would you control that? So you have this limitation. If you send more in, there will be toxicity. It will be bad for your health. Everyone will sue you. If you send less, you will not utilize the tunnel enough. You will have big traffic jams. Everyone will sue you anyway. So how could you do that? So you have 3,600 per hour. So okay, let's scale down. Let's have 16 liters per minute. So that means 1 liter per second, right? Well, of course, no. So what happens when 12-liter truck arrives? So will you wait 12 seconds? What will you do? So we can't really scale down to this 1 liter per second because we need to cope with the inherent burstiness. So we need to take the largest unit available and so on. So going so deep to gradually scale this small, it's impossible. Okay, let's scale one step up. Let's go 60 liters per minute then, instead of 1 liter per second. So what happens when you have 2 minutes and there's no traffic whatsoever, and then a row of the cars worth of 1,500 liters arrived because they were stuck after the lorry, as they usually do. So what should you do? Should you send all 150 liters to pass based on that the previous 2 minutes were empty? Should you pass 100 liters based on that the previous 1 minute was empty and leave the 30 liters queued? Or you just ignore all the previous 2 minutes and send only 60 for this minute and leave the next 90 for next minutes? So that's the decisions that when you're doing with throughput, applying the queues, actually the queuing needs to make. So simply people don't realize. But if we take a look, so this is actually like 1 hour here. And if we take every minute 60, 60, 60, 60, and then there's 2 minutes with nothing, we will underutilize the tunnel in this way. If we will sense, so in this case, if we take 1 hour from that moment to this moment, it will look underutilized. So because 1 hour can start at any given time, because it's not specifically that it will start at 00 and will start at 1100 and finish at 1200. It can start at any moment. You can start measuring like just a minute before that happened, and it also will look underutilized. In this case, see, 2 minutes without cars, and then we send 150. But then 3 minutes passes, and you have 150 minutes in first measurement minute, and already you exceeded the specification of your tunnel. This is, by the way, the reason why some of you, when you have a queue of 20 megabits, sometimes might see 22 megabits passing through it, because you just looked at the queue at this moment over here. So that's why these things are not so precise when you look at the queue statistics, numbers, and so on. It really depends on what moment in time you look at it. So, and basically, if we don't do the burst over here based on previous 2 minutes, we will underutilize the tunnel from 2 points of view, and it will look quite nicely when we start looking from that last minute. So, what to do? How can we implement that perfectly? So that means that we can't really scale down to 60 liters per minute. And we can't just use 3,600 liters per hour, because we will run out of the 360, and then the next unlucky car that has this 3,601st liter will have to wait for the next hour to next 36 starts. So it will be very, very bursting, and that guy probably will jump out of the clip waiting for an hour to get in the empty tunnel that has been empty for minutes and so on. And again, as I previously showed, you don't know where that hours actually starts from that perspective. So the conclusion is very simple. I think I illustrated quite nicely that traffic is too chaotic and unpredictable to apply any type of scaling directly. So scaling is not an option for the queues. And for the tunnel here itself also. So the solution is actually to apply a token solution. So you place a toll booth before the tunnel. It will generate a token at any given time scale, it can generate 1 token per minute. It can generate 0.1 token a tenth of the second or something like that. It doesn't really matter. It scales perfectly. It will be able to accurately limit number of tokens. So as a buffer, cars will have to get a token to pass. And when you calculate that buffer size for tokens that's already accumulated in the toll booth, you need to take into account the token rate. So for example, as I told you previously, so to make sure that you don't get over this number, you need to calculate your limit, your available burst, and your limit in here. So for example, not allow 60 cars, but allow 59 cars all the minutes, so then you can better cope with the bursts if they happen in the future. So, and why I was telling you all about these tokens and so on, because that's how the actual queues and throughput works in a MikroTik. So all the queues work with the tokens. So we don't do anything with the traffic. So the blue part of the diagram is how the traffic passes. So traffic doesn't do anything else than arrives, stands in the queue, tries to get a token, and then just passes through. So same as the cars before the tunnel. But all the algorithm on how to calculate the speed, the megabits per second, happens in here and is based on the tokens. So all the limits that you apply on your traffic is not actually applied on the traffic. They are applied how you generate tokens that your traffic then you can use afterwards. So if you have this way, if you have a proper token size and bucket size, for example, if you didn't have any traffic for let's say 10 seconds, and you have a 1 gigabit connection, and you have 100 megabit limit on the queue, but for last 10 seconds you didn't do anything, your next traffic will actually be transferred at 1 gigabit per second speed, because they have enough tokens to send it through. So that means that your traffic is not actually binded to 100 megabits all the time. Your token rate is banded to 100 megabits per second. Your traffic will be very bursty and so on. So there's a big difference if your connection is fast Ethernet or gigabit Ethernet in those moments when you don't utilize it all the time. So basically, if we go back to tunnel analogy, it's the maximum allowed speed through the tunnel. So either it goes 10 miles or 100 miles per second, per hour, sorry, through the tunnel. So that's the difference, so that gigabit per second connection is actually better than 100 megabit per second connection speed, even if you limit it below that number. So all this information is available on wiki page, so I hope I got at least your interest to dig a little bit deeper into it. But just realize, guys, that when somebody talks about limiting traffic, they are actually not talking about directly limiting traffic. So they are talking about issuing the tokens, and then the traffic either will pass or will be dropped based on the situation with tokens and the queue size. Okay, let's go back to the real network speed. And most of our customers, usually when they complain that you don't offer enough throughput, so they paid for 150 megabits, but you're only getting 100 megabits to them because this guy over here, this web page says that there's lower number there. So, yeah, that's actually my second favorite page on the whole internet. So, but not many of you of us administrators have actually looked into how exactly that speedtest.net works. So if you go to their homepage and look on the page that calls how does the test itself work, how is the results calculated. So link is below, so you can look it up yourself. So speedtest.net will use up to 4 HTTP threads. So after the pretest, if the connection speed is at least 4 megabytes per second, speedtest.net will use 4 threads. Otherwise, it will use 2. So if that means that speedtest.net always advertises that it has multi-connection test. Instead of multi, they should just say 4. So it's a 4 TCP connections. One side sends initial chunk of data. The other side then calculates the real speed. So they're not actually sending you the speed. They calculate the speed based on the chunk of data that was sent. And they send that in real time many, many times and do that calculation. From all the samples, they are sorted by speed. The 2 fastest ones there are dropped, and the bottom 1/4 then are removed, and whatever left is averaged. So is this a real network throughput? So just a food for thought. So maybe to indicate something to your customers when they send you this screenshot from speedtest.net. So how it actually works. And also it's a 4 TCP connections. So let's go back to the good old TCP IP Bible. I tried to narrow the whole 800-page book to the 4 slides. So excuse me. Excuse me if there's some imprecise data. So it's intentional. I just trying to get main points across. So basically, TCP throughput is limited by 2 windows. Congestion window, it's on sender size. So that's basically amount of unacknowledged packets that may be in transit. It auto-tunes based on congestion control algorithm. And it's very impacted by packet loss and by delays. And there are many algorithms. There's not a single one best. MIT is coming out with new ones every few years. So, and actually the sender size, the software solution decides what congestion algorithm they want to use for their TCP connection. So you don't have any impact. You cannot change drivers or something. It's actually the application itself chooses what congestion algorithm it will use. Second window is receive window. So on the receiver side, it's the amount of received data that's not processed yet by the application. So, and it auto-tunes based on the receive buffer size and its level of fullness. So that means that how much data was actually processed by the receiver. So sender and receiver negotiate this common transmission window, 2 windows actually for both sides. Even the replies or ACKs will have their own window. So you have one window for transmit, another window for receive. And maximal single TCP stream throughput is limited to not more than 1 full transmit window in a round trip time period. So middle devices like our routers only have indirect impact on this congestion algorithm uses. So we impact round trip time, we can impact jitter, we can impact also packet loss with the queues. And if you want to calculate yourself what's your maximum single stream TCP, you can always use a Wireshark, sniff TCP traffic, and you will see these 3 options over there. So window size value and window size scaling factor. And if you multiply one by another, you will get this calculated window size. Then you can use that calculated window size and divide it by round trip time, let's say 6 milliseconds. You can get that with this size and this round trip type, this TCP connection theoretically can only achieve 25.26 megabits per second. So even if you have a gigabit per second connection, wire speed connection and so on, both ends, so the receiver and the sender, communicated and decided that maximum speed, possible speed is this. So how does the TCP traffic is your real internet throughput traffic? Because routers has nothing to do with it. The actually sender and receiver are the ones that tries to calculate it. And if you have really large buffer, like I have in this example, so 4 million something, and round trip type 60 milliseconds, then you can receive, for example, 563 megabits per second maximum on that single connection. By the way, this is very unlikely. This is actually satellite link, because where would you have a 4 megabyte receive buffer available for the driver and so on. But you can always sniff and check yourself and calculate yourself. It's very easy to calculate. Just ping it, sniff it, and divide one value by another, and that's your absolutely maximum that can be achieved by that single TCP connection. Also, when we're talking about TCP, many guys were testing TCP throughput with our bandwidth test utility, and were complaining it's limited to the single core. That's the problem. That's why we have a slow internet. That's why MikroTik slows everything down. Well, it's not true, actually, because TCP doesn't like multi-threading. Because multi-threading introduces out-of-order packets. Usually, TCP can handle out-of-order packets within that single transmission window. But if you have some out-of-order packets between those two windows, they might consider that traffic is lost, delayed, round-trip time is bigger than it actually is, and so on. And as you saw in previous calculation, bigger round-trip time, lower the maximum speed. And the windows might be negotiated differently. So let's visualize. So for example, you have 4 cores, you have 4 packets arriving. Those cores, of course, are busy with something else. Also, there's another packet traffic going on, or they are limiting something, encrypting something, doesn't really matter. CPU is doing something all the time. So it might be a situation when the first packet arrives, it just gets processed instantly. The second packet gets partially processed, then it needs to wait for CPU time, and then finishing up. The third, on arrival, CPU was busy, that a different core was busy, and the next, only then packet was processed, and so on. So you might end up in completely different sequence than your packets arrived to the router. So that is why one TCP stream tries to stick to one CPU core or thread. And this is actually called flow packet steering. So RouterOS uses flow packet steering to assign incoming traffic to specific CPU core thread. And it's based on hash value. So that hashing can be either hard-coded in the hardware, and we have no control whatsoever how it works. So the CPU decides itself which core it assigns traffic based on the hash values. For example, one of the CPU calculates source destination address and source destination port, all 4 as a hash, and then distribute them by cores. Then there is a possibility to configure it in the hardware, where we can actually go into the hardware and check which fields will be used in the hash to distribute the traffic between the cores. And the latest option is that we decide ourselves how to distribute traffic based on these hash values between the cores. And basically the steering in all our products will try to keep single TCP stream bound to single CPU core thread as long as possible. So it's possible when you receive very high speeds and CPU load gets, single core load gets 100%, then it will jump to use the second CPU. But in most cases, it will result in slower speed and it will fall back into single CPU again. Anyway, just to show you an example, so this is 3011. And 3011 hardware feature is that each switch chip has two connections, one connection to each CPU core. So we are actually making a decision over here what to send to one core, what to send to other core, just because of this specific structure of 3011. So we had to make that decision to utilize both 1 gigabit lines here. So just to summarize, what can we do, what can't we do? So we can't choose the congestion control algorithm. So that's by sender size program. And we can't determine the congestion and the receive window sizes of the endpoints. We can change MSS, maximum segment size. We can minimize impact on round trip time by reducing packet processing time. And we can impact packet loss for the TCP traffic. So just a reminder how routing works. So there's lots of processing for the simple routing going on through the router. So if you take a look at packet flow diagram from version 6, so big diagram, if we dive deeper, you see how packet processed through the router, and we can go even deeper. There's lots of things that packet goes through to get routed through the router. And I want to just remind you that there's a way to minimize that processing time through the router. It's called FastPass. We have that implementation for quite some time. I've been talking about, I think, forever in all my presentations. So basically, there's a way to skip all the processing. And if you enable FastPass, you can just rely on routing decision. And if there's no configuration in any of those boxes, you can just process packet much more faster. So, and there is extension for FastPass. So these slides are actually from my previous presentation. So if you are interested more deeper about, just watch those presentations. So, and also we have more commonly popular way to fast pass traffic when you use connection tracking. This is called fast track. So the faster connection is actually an action in the firewall where you can mark your packets as fast tracked. And then they will follow the fast pass way through the router. It only works on TCP and UDP of IP version 4. And you will be able to see the numbers, what is actually fast tracked in the connection tracking table. So, and it works very simply. It just looks at connection tracking and just sends packets to FastPass. So why I'm showing you this, so if we take a look at 2011 and we disable fast track and FastPass support and use only single TCP connection, we were able with default home AP setup. So if you go to this quick set and use home AP, which has a default firewall and access point and so on, single TCP connection was able to achieve 358 megabits per second, and they bottled at the CPU load 100% because the firewall was taking 44% of that CPU. And if we enabled fast track, the same hardware, same rule set, same everything, where it was able to get 890 megabits per second single TCP connection throughput just by reducing round trip time, because the CPU is not bottlenecked anymore, because the firewall uses much less percent. So that's one way how you can improve your real throughput for your customers. I mean, speed test results get better. Second thing that we also need to consider is how full queues and multiprocessing works. So when you have queues, packets actually spending most part of the processing time waiting in those queues. So in order not to waste CPU cycles, current core will just leave the packet in the queue and will take out already processed packet out of the same queue. So basically, one CPU will swap packets. So one CPU will leave it, the next CPU might take it out. So queue packets are taken out of the queue by random core that works at that queue at that time. So that means that if you have queues that actually limiting traffic, it will shuffle CPU cores that work with that TCP traffic. And do you remember what happened when we introduced many cores working with the same TCP stream? Out of order packets. So actually that will have the biggest impact that your actual queues on your TCP stream. Second thing, if you have empty queues, then in our current implementation, CPU will just leave the packet in the queue, and if the queue is empty, then it will take the same packet out, so there will be it will stick to the same CPU core, and basically your TCP will not suffer because there will be no reassignation, so on. So conclusion, queues don't actually slow TCP streams if they're not actually queuing the packets. So if the limits are not reached, and if they are reached, they screw TCP twice as hard as they do with UDP. The complexity of the configuration have a minimal impact on the TCP stream, with an exception, of course, of deep packet inspection like layer 7 or content. And you are fine until TCP core or thread doesn't reach 100% load. If it does, then think about fast tracking and such things. So you can use FastPass, Fast Track, IP Firewall Raw, and other options to reduce overall CPU load. But until you hit 100%, you are fine. You are not slowing down the TCP IP performance, maximum performance, and so on. So, and we are closer to the end. Let's talk about testing from the router to the router. So traffic generation and elimination takes at least the same amount of CPU resources as simple traffic forwarding. So you use half of the CPU, if not more, to generate traffic when you test from the router to the router. So if you max out CPU, that doesn't mean that you tested your throughput of your device properly, because it was generating the traffic. Also, you need to understand that forwarding process has the highest priority on the routers, because that's the main job of the router, to forward traffic. So that is also the reason why pinging through the router usually is faster than pinging to the router, because we are prioritizing pings and traffic through it, not the replies to it. So that might be the very unlogical thing, that pinging something that's 4 routers further is 3 milliseconds, but pinging the first router closest to you, it's 6 milliseconds. So it simply means that your router is quite loaded and it's busy with routing traffic instead of just replying to some stupid pings that's sent to it. So when we're testing from router to router, we have very nice tool. It has many features. It's traffic generator. You can set traffic rates. You can determine packet losses. You can detect out-of-order packets. You can collect latency, jitter information. You can even inject a captured PCAP file, so to check your firewall effectiveness. There's a quick mode. There's also full Winbox support that can be improved a little bit, but it doesn't have a TCP protocol support, and for some reason it scares people. So hardly anyone uses that. And then there is a other tool. So first of all, bandwidth tool, everyone loves it. So until version 6.44, it was single-threaded. And now both UDP and TCP tests actually support multi-threading. So we also added a warning message that informs you that the CPU exceeds 90%, to inform you that your link is not the bottleneck, but your CPU that generates or receives the traffic is the bottleneck. You can now do multi-stream test, but always the question that you need to think about, how many should you do to properly test your throughput? So what can be the answer? Should you do one? Why four? To do the same as a speed test? Well, I would say that you probably need some minimal number, and you definitely need at least one per CPU core or thread that you have on the router. So if we're talking about 1072 CCR, that you need 72 threads, 72 connections to test it properly, to generate it properly. So if you have lower number of CPUs, I still suggest to stick to 20 or above, just to eliminate all those TCP window and so on problems. So just to answer your question, we also decided to make additional tool, which is nothing fancy. It's based on ping and bandwidth test in new implementation. We call it speed test tool. The name is intentional to confuse everyone. So it's a simple tool that measures ping, jitter, TCP and UDP throughput, and it automatically then determines the optimal number of test streams based on CPU core count of both devices. And it's in command line interface, and it looks like this. So just type speed test and address where. So both devices need to have 6.44 or above. It will give you ping, mean, average, max, jitter, mean, average, max, your loss, and TCP download, upload with the megabits per second, and CPU load on both ends, and so on. And if you reached the limitation, it will give you the note that your results might be impacted by the CPU. So I think that's the quickest and optimal way for you to test the actual throughput. I hope that you found this presentation interesting, and I hope you have a different perspective of things. So thank you.
Thank you. Any questions? Yes.
So there's a, because of the token situation for speed limiting, there's a mention somewhere in the settings, and I forget exactly where, that you can set a burst period. So how is that affected with token generation?
So burst, if I can jump back to the diagram. It's cool. Yeah, here we stop. Ah. Yeah, buffer overflow. I used too much tokens. So yeah, here we go. Burst option is used in this algorithm over here. You can go into the wiki and take a look. So if there's actually what happens when the burst is allowed. So the token rate will be generated at the burst limit rate for some moment of time. So that calculations go there. In latest versions, you were able to specify the bucket size. That's the thing that we added for you to change. So any more questions?
I'm just curious about the, when you're going over the speed tools, the ping speed tool under the advanced tools package, how does that one work?
Wow. I think it just sends a ping with different sizes of packets and then calculates the difference, how fast the smallest packet was received compared to the longest packet, and then multiplies that result enormously to get you the result. So it's really imprecise thing to do, but that's how somebody does that.
Good morning.
Morning.
So now that bandwidth test is multi-threaded, when situationally would one want to use bandwidth test versus speed test? And is there any plan to add the speed test to the web UI or to Winbox?
So the first thing, the speed test is exactly the same as a bandwidth test, only with preset number of connections. So you will get from 20 to so not less than 20 and not more than core count of connections in speed test automatically. You can manually set it if you want. Speed testing, bandwidth testing, single connection from router to router, where the congestion window is calculated by the routers themselves, doesn't reflect in any way what TCP connection will work from the customer application to another server application, because they are completely unrelated to each other. So, and about web interface, I hope that you all guys will write to support that you need it, and then we will collect the numbers, and as usual, the most popular features get implemented. So that's how it works, but I think that we are more used to typing in IP addresses in command line anyway, and it will be much faster, much easier in the command line interface, at least for me.
So what would you recommend, since you said forwarding has the priority, so you'd want to put a MikroTik on the backside. If you wanted to touch a 500 meg circuit just to kind of confirm the numbers, the jitter and all that stuff, what would you recommend as the MikroTik to use for doing that test?
Usually I connect the good big CCR on both ends, or if I have it on the test bench, I can connect both ends of the link to the same CCR and use a traffic generator, because traffic generator traffic needs to return to the same device to get a precise measurement of data. So I would use that. I usually test everything with the CCRs and traffic generator. It doesn't really matter. Each core is actually exactly the same core in the 9 core as in the 72 core. There's only more of them. So if you need a 10G connection, of course, you go for the CCR with 10G interfaces. And if you don't need that, just go with the simple ones. So just make sure that you will run at 1200, because higher core count runs at 1 gigahertz only. So lower core count CCRs run on 1.2 gigahertz. So that might be the difference between CCRs. So anyone else? So if you have any more questions, I, as usually, will be available on the front desk. So thank you.
Thank you.